Hi, if you are a computer nerd who's into music like me and you like hacking stuff, I definitely recommend getting MC-707, MC-101 or MV-1. I think the fun with them is just endless, and not only music-wise. All the software that I created for my experiments is available on GitHub under a free license. This way, you can analyze my software further, recreate my experiments, or use the software for your own creative projects. I developed the code for my hacks mainly considering MC-707, but you probably know that MC-101 will work similarly or the same, but with the limitation to 4 tracks instead of 8. The MV1 is maybe not entirely the same, but in many aspects it's very similar. The low-level MIDI and Sys-Ex communication over USB works the same in MC and MV Grooveboxes. Just set the USB driver in your Groovebox to generic. However, the 5-pin MIDI DIN communication in MV1 is limited to only writing the Sys-Ex messages to the instrument. I only briefly tested it, but the ZEN-Core Sys-Ex sound editing seems to work the same in MC and MV. From the USB host point of view, the main software is still primarily intended to be run on Linux. Since my previous video about the ZEN-Core editing using Sys-Ex, I think I improved the software a bit, especially the communication part of the driver. First of all, I switched entirely to USB communication, so if you have a computer with a Linux operating system, you probably won't need any extra hardware to communicate with the Groovebox. I also implemented the communication using 2 different drivers, ALSA commands and Python Mido library. In case of the ALSA communication, I just call the ALSA commands for Linux as subprocesses from the Python script. It's slow, but I think it works quite reliably. In contrast, when I use the Mido library, it works super fast compared to ALSA option, but in my case, it hangs internally at random times, especially when I read and write lots of data. Anyway, I'll share both implementations, and you can select whichever you prefer by just instantiating the driver class with ALSA or Mido string as the constructor argument. By the way, the Mido bug might be somehow related to the discussion, which I link in the description. If you don't have a Linux computer and you don't want to deal with virtual machines, then you can get a regular Raspberry Pi. It doesn't even have to be any cutting-edge one. However, the larger form factor version will be preferable. That's because the larger ones are just easier to configure and to use. And they can work decently fast with the graphical user interface, so you can more easily visualize your sequences or motion. But if you plan a very minimalistic user interface, you can be good even with the least expensive Raspberry Pi Zero options. I successfully ran the communication, the sequencer processing code and the matplotlib visualizations on Raspberry Pi 3B+, and I did it literally without any modifications to the script that I developed on my Linux PC. The basic modules work the same, I just needed to install basic drivers and libraries with a couple of terminal commands. And if you are okay with installing them system-wide, you don't even have to deal with Python envs and stuff like that. As the supplementary materials to this video, I share a little software project that I created. It contains Python scripts with the improved basic communication implementation, the improved Sys-Ex memory dump tools, and the simple compare tools, which can be useful if you want to figure out more possibilities that I present in my videos. I also included the ZEN-Core parameters modification code from my previous video, this time implemented in the form of a class. In most cases, you can run some basic tests by executing each tool script as a main module. I tried to include some simple test code in most of them. Here I show you the new example from my last video about ZEN-Core control over Sys-Ex, but this time using more friendly and more object-oriented version of the script. I also tested it on MV1 and it worked too. Here you can see the ZEN-Core class definition. I ported the course tune modification code to the new implementation that you see here. And here is the part of the code that gets executed when you run this module from the command line. It creates an instance of the MIDI interface class and creates the MIDI object. By default, it uses the slower but more reliable ALSA driver. The MIDI object is used by the Sys-Ex communication class instance, the COM object. And the Z-Core object of the ZEN-Core tools class uses the COM object. Here we change the course tune parameter 5 times, about once per second. I developed the hack tools to discover the new areas in the MC and MV address space. If you don't know where to look for changes in the instrument's memory after you record something or change a parameter, you can dump the memory twice and then compare the dumps. I included an example that does exactly that. In this example, a part of the memory space is scanned twice, and each time you get a separate dump in the form of a CSV file. Also, the tool has the listDiff method that lists the changes detected in the scanned area. But be careful with it, because if the instrument starts to respond to new locations of the area, they will not be listed by this method. That's why it's preferred to use some kind of external diff tool. The hack tools can call the diff or compare tool automatically. It can use the gathered dumps as the arguments so that you can inspect the differences visually. Here is the example of comparing a part of the settings area to detect what changes inside the instrument memory when you modified colors assigned to each track, but for the first 4 tracks. I plan to show you more of such features in the next videos. Thanks for watching, and if you are interested, please stay tuned for my next video in which I analyze the sequencer of the MC and MV Grooveboxes. See you!